Chemical Kinetics Part 12, half-life for a second-order reaction, and we're going to do a quick review of 0, first, and second-order half-lives. This is a sheet with all of the important equations that you would use to do calculations for kinetics. In this video, we're going to take a look at how you can take the integrated rate law for a second-order reaction and turn it into the half-life equation for a second-order reaction. So when you have a second-order reaction, we're going to start with the integrated rate law for a second-order reaction and substitute in for concentration of A at time t 1/2 the concentration of A at time 0. That's the criteria when the time is equal to the half-life time. So we substitute that in the denominator here for concentration of A at time t. And now we're going to call the time t 1/2, the half-life time. What we can do here is take that 1/2 and put 2 in the denominator, because the inverse of 1/2 is 2. And then we can subtract the inverse of the initial concentration, or the inverse of concentration of time 0 at time 0 from both sides, so we get it over on that side. Now the rule of fractions is that when the denominator is similar, we just subtract the numerators and carry the denominator over, so the left-hand side solves out to be the inverse of the initial concentration. And then we rearrange to solve for t 1/2, and we get this half-life expression. Notice that as the initial concentration, or concentration of A at time 0, gets bigger, the half-life gets smaller. All right, so a quick review here. Half-life is the time when the concentration is equal to half of the initial concentration. You have half of what you started with. In a zero-order reaction, we get this expression, and you can see that as the concentration of A at time 0, or the initial concentration, gets bigger, the half-life gets bigger. When the numerator gets bigger, the value gets bigger. Here's a first-order half-life expression, and notice that since k is the rate constant, any number divided by a constant is constant. Half-life is constant for a reaction, and that's, at a given temperature. Of course, k is temperature dependent, so we're assuming that it's constant at any given temperature. And this is important for radioactive decay of elements. They typically follow that. And then for second-order reactions, here's the half-life expression. And notice here that as the concentration of A at time 0, or the initial concentration, gets bigger, as the denominator gets bigger, the value of the fraction, the half-life, gets smaller.